we did the composition, we got x in both directions. Those are functions called inverses. So first of all, we'll talk about why inverses are useful in terms of inputs and outputs for some specific situations. So have you seen this formula before? V equals 4/3 pi r cubed. This is the volume of a sphere. You don't have to have it memorized for this class, although I can tell you that your calculus class might make you memorize it if you take calculus class, okay? You actually prove that the volume of a sphere is that using calculus. Yeah? Oh, we were going to do that one last example. We'll go back to it at the end. So the volume of a sphere is 4/3 pi r cubed. And does it make sense that you input an r, or a radius, and then what comes out? You get out, well, specifically you get out the V or the volume. Does that make sense? Like once you know R, you can find the volume. You input a radius, out comes the volume. Does that idea make sense? Okay. How about this formula? F equals 9/5 C plus 32. What does this formula do? Do you know? It converts degrees Celsius, right, into degrees Fahrenheit. So in the words of inputs, outputs, you input temperature in which degree subsystem? In degrees Celsius, and out comes the temperature in degrees Fahrenheit. So you would use this as an American in Europe to understand how hot 30 is.
I'm an engineer, I use Kelvin.
Okay, well, you're special. So input a temperature in Celsius, out comes temperature in Fahrenheit. So no, but what if you were a poor European who's stuck in America and you're like, oh my God, what is this? Like, minus 20 we speak of, right? So you might want to reverse this correspondence, and instead of inputting Celsius, you want to input Fahrenheit. Does that idea make sense? You want to reverse the correspondence. So these are the inverse functions of the two things listed above. So in part A of example 1, we input a radius and out came volume, right? In this one, what is this doing?
Input volume to the radius.
You input volume and your output is radius. You see how that flip-flopped? And also input is X and output is Y, right? So you reverse the roles. You reversed who was X and who was Y. And suppose you have a whole bunch of spheres and you want to find their radii and you know their volumes, this is what you would use. Okay, how about this guy? What's this going to do?
Input Fahrenheit, Celsius.
You input degrees in Fahrenheit, and your output is degrees in Celsius. So inverses let you reverse correspondences. Take what was X and make it into Y. So one specific example we'll talk about in Chapter 5 has to do with exponential growth. So for example, if you invest money, it's really easy to figure out how much money you have after a certain time. But it might also be useful to figure out, when will I have so much money? When can I retire? That kind of thing. Of course, that's all on your minds right now is when can you retire, and you haven't started working yet. But, okay. So, reversing the correspondence often produces a new and useful function. This reversed function is called the inverse. You can roughly think about it as kind of an opposite function of some sorts. And we are going to develop methods for finding these functions in this and the next lesson. And before we begin, we need to know something called a one-to-one function, because not every function has an inverse. Some functions don't have inverses. So here's the definition of a one-to-one function is. A function is one-to-one if no two ordered pairs in the function have the same second and different first components. So what this one-to-one means is that one x goes to one y. You can't have two x's going to the same y. Does that make sense? So that's what one-to-one, one x to one y. So for example, x squared. Is that 1 to 1? Does every x go to its own special y? No. Yeah, this is not 1 to 1. And the reason is when you plug in, so say you can make this into function notation by saying, well, y parenthesis -1. That's -1 squared, which is 1. And y of 1 is also 1. So both -1 and +1, we'll say go to +1. Does that make sense? In terms of the whole like potato picture, that's like saying, okay, -1, 1, both go to 1. That's okay, you can be a function, like if you do that, that's totally fine, but you're not a 1-to-1 function. 1-to-1 functions are special, and that one's not special.
Do we have to show our work to show us a 1-to-1 approach?
No, there will be a very easy way to tell. Okay,
Well,
so
like if we were on a test and to get full credit, we have to show our
there will be a very easy way to tell. Okay, like just give me like 5 minutes and we'll get there. How about 4 minus 2x? Does every x you input give you a special y?
Yes.
Yeah. One way to figure that out would be to look at the picture. That's a line up 4 with slope of what?
1 to 2.
So down 2, forwards 1. And since that line doesn't double back on itself, every single x has its own special y at a special unique height. So this one is 1 to 1. Yes?
Is there a way to figure that out without having to draw a picture?
You can draw a picture in your head.
It's so much.
That's so inconvenient that you have to draw a picture?
Yeah, like every time if you have a question like that, there's something you can't do.
Well, you can tell it by exponents, or by plus or minus.
Like if it gets more complicated,
absolute
like that's
value.
easy to picture, but
You're only going to be given things that are pretty easy to picture. Like, what does 4 minus x squared look like?
It's a sad parabola.
It's a sad parabola shifted up how much? 4. Crosses the x-axis at plus or minus 2, right? And from that picture, you can tell that when you, say, plug in, I don't know, this x and this x, you get the same y, right? Which means 2 different x's went to the same y. So are you 1 to 1?
No.
No. So yes, the easy way to tell is actually looking at a picture. So yes, you have to draw pictures, but you're only going to get stuff that you can draw pretty easily. I'm not going to give you something super wacky.
What about root 9 minus x squared?
Root 9. That one's not ridiculously wacky. We'll get there, okay? We talked about that one before. Okay, so here is a little theorem about 1-to-1 functions. So if f of a equals f of b for at least one pair of domain values, a and b, then f is not 1 to 1. So what this is saying is if 2 y's are equal for different x's, then your function is not 1 to 1. My space wasn't as long as yours. Kind of like the parabola function when you say plugged in just x squared, when you plug in +1 and -1, they're different x's, but they give the same y. Another way to say it is that if you assume that f of a equals f of b, so if you assume that 2 y's are equal, that means your x's were equal. So if 2 y values are the same, they came from the same input / x value. So a really, really, really easy way to tell if something is a function is to use something called the horizontal line test. Remember the vertical line test? That told us whether something was a function by looking at its picture, right? So if you have a graph of a function and a horizontal line hits it more than once, then it's not going to be a one-to-one function. So that's what this thing says. This is the test that you should use all the time. So a function is one-to-one if and only if every horizontal line intersects the graph at most one point. And so here's why it's the same thing as the theorem above. Suppose you had a picture, looks like that. And if you have a horizontal line that hits it in two places, that means that two different x's give the same y. And that means it's not 1, 2, 1. You're not going to be given stuff ridiculously wacky. A lot of the way that they're going to test these questions is they're going to give you a picture and say, is this a one-to-one function, yes or no? So every single straight line, is that a one-to-one function? Yes. Except for horizontal lines. Does that make sense? Okay. Every single parabola, are they one-to-one functions? No. How about x cubed? Just think in your head what the picture looks like. Yes. How about the cube root function?
Yes.
Yeah, okay. What else did we have? How about the square root function?
Yes.
I think that's okay. Yeah, the root function, it looks like this, right? And so if you think about taking your pencil and like running it up the graph, the horizontal lines are only going to hit it once, right? Here is how that's related to the vertical line test, because it is definitely related. So those first examples that we had, we talked about volumes and radii and volumes. You switch the correspondence, right? So if you tried to find the inverse of x squared, which looks like this, if you switch the correspondence, you get x equals y squared, right? And that makes a sideways parabola that looks like this. Is that sideways parabola a function?
No.
So you have to restrict it, yeah. So you can still make an inverse if you only look at part of the parabola. Just look at the positive part usually. And then you'd say, okay, well, it's just that part only. But the idea is that if your function doesn't pass the horizontal line test, when you switch an x and y, that thing won't pass the vertical line test. That's how it's related to that vertical line test. Okay? All right. So, be super fast, use the horizontal line test, tell me whether the following functions are one-to-one. I want a rough little sketch of what you've done, like just a little bitty one. I'm not going to grade perfection, but this is a parabola shifted up to. Okay, so is this one-to-one, yes or no? No. Does it make sense that if you had x's bigger than or equal to 0 only, then it would be? Does that make sense? Okay, so that's something that will actually happen. So if they give you x squared plus 2 and they specify that x is bigger than or equal to 0, then you would say, yes, it is one-to-one, because you're only looking at positive x's. How about square root of x minus 3? So that's a root function. How is it shifted?
3 to the right.
3 to the right, exactly. So 1, 2, 3. And it's got approximately that shape, right? Okay, so is this one-to-one?
Yes.
Yes. If I don't specify to show your work on your quiz, you can just say yes or no. Does that make sense? Like, they're probably going to be like 1-point questions because it's really, really easy to tell. Okay. So let's talk about how to find an inverse. So we'll start with some point things, and then we'll do some actual equations. So tell me whether the following functions have inverses, and if they do, find them. If not, explain why not. Give the domain and range of both. Okay, so if you were to see if it had an inverse, you have to see is the function first one-to-one. So in the domain of this first function, we have-- 0, and 3. And 3 goes to 9, 0 goes to 0, and positive 3 also goes to 9, is that function 1, 2, 1? No. So no, not 1, 2, 1 has no inverse. So don't pass go, don't find inverse. This one, 1, 2, 3, so 1 goes to 2, 2 goes to 4, 3 goes to 9. Is that function 1, 2, 1? Yes. Okay, so if we call that relationship F, the domain of F is all the x's. It's 1, 2, and 3. The range of F is all the y's, which are 2, 4, and 9. Now the inverse is just going to do the opposite thing. If this function takes 1 to 2, the inverse undoes that and takes 2 back to 1. So 2 goes to 1. Where does 4 go back to? 2. And 9 goes back to 3. And the notation for that is F with a little negative 1. Like that little negative 1 means inverse. What is the domain of that inverse? 2, 4, 9. Or it's the range of F, right? What is the range of F inverse? 1, 2, 3, or the domain of F, right? So reversing these correspondences, yeah.
So even though there wasn't one for the last one, there wasn't an inverse, we still have to put the domain and range because it says give the domain and range for both. Or would it be okay?
I think that this implies, so you're saying, do you have to do the domain and range for part A, right? Is that what you're saying? Yeah. I think since that last sentence says give the domain and range of both, if you don't have both, you don't have to. But that's something that's probably a little bit specific. My main point was I just want to show you with some actual points that these things flip-flop. Does that make sense? Technically, also to write the function, you have to list them as ordered pairs. Like you'd have to list the inverse would be the set of ordered pairs 2, 1, 4, 2, and 9, 3. Like technically that is the inverse. You could kind of think also that probably what's happening here is that, oh, that's not quite it. It's definitely not squaring. No, okay, stop. 1 squared is not 2. Okay. Stop. All right, so the whole reversing correspondences thing makes sense. That's the main point of that. All right, here's the definition of an in function. So if f is a one-to-one function, then the inverse, denoted by this, so f with a little power of -1, is the function formed by reversing all the ordered pairs for f. So f has certain xy's, the inverse just takes them all and flops them. What was x becomes y, what was y becomes x. And so f inverse is the set of all points, x, y. That's wrong. That should be yx, such that xy is in f, as in they've been flip-flopped. And if your function f is not one-to-one, then f does not have an inverse, and you just say that f inverse does not exist, unless you restrict your domain. And just one thing, I don't know why they chose to use this notation, but this notation, when you see like 2 to the -1, that means 1/2, right? We made you drill that into your head forever and ever and ever, and now I'm going to tell you that for this thing, this is not the same thing as 1/f. Okay, so that notation means inverse function, but it's not the function 1/f. If you want to write 1/f, so this thing means inverse. If I put parentheses around f of x and then put a -1 on the outside, that means 1/f of x. And I apologize for the fact that the notation sucks, but I'm afraid I can't change it and it's used so ubiquitously, you just have to know it. It's like a mathematical vocabulary word, I'm so sorry.
What would the inverse of a function look like if
not this class.
Okay.
Okay. Alrighty. So here are some properties, and we'll go on to finally find some inverses. So the first thing for a given function f, if f inverse exists, then f inverse is also a 1-to-1 function. If f is 1-to-1, so is its inverse. The domain of f inverse, we're flip-flopping, so the domain of f inverse is the range of f. And the range of f inverse is the domain of f. So basically with inverses, x and y switch places. Okay, so for this function f, find f inverse. So 3 goes to 5, 7 goes to 11, 11 goes to 17. It definitely is 1-to-1, so it has an inverse. So what is the inverse? What inverses do to points? 5, 3. What's the second point going to be? 11, 7. And what's the third point going to be? 17, 11. So for that function that was just defined for 3 values, that is the inverse. So your part B says, what do you think the result of composing f with f inverse will be? Or vice versa. And we're going to just try some values. So suppose I did f inverse of f, and what's a number that I can plug into f? Only 3 options, right? What are they? 3 into f. So 3 or 7, right? Or 11. So I do f inverse of f of, say, 3. So first figure out what f of 3 is. What is f of 3 going to be? 5. And then what is f inverse of 5? I think of inverse functions like my little sisters. I did something, and then they would undo it and put me back where I started. I'm sorry, Maggie and Katie. So there were also 2 of them. It was totally not fair. So let's try, maybe 3 was special. Let's try another one. F inverse of f of 11. So that's f inverse of, what's f of 11? 17. And what's f inverse of 17? 11. Do you see what I mean by like undoing, like opposites? This f inverse seems to undo that f. Does that make sense? That's what inverses do. That's their job in life, is to undo each other. Okay, so, but also order does matter to composition, right? So let's just try one the other way. Let's try f of f inverse of some number. So what numbers can get plugged into f inverse? 5, 11, and 17. Let's do 11. So that's f of 7, right? And what is f of 7? 11. So when you do a function composed with its inverse, you just get back x. And that is called, that function x is, or whatever, is called the identity function. That's how you check and see if 2 functions are inverses. So that's the next theorem. So it's inverses, and did that already. So inverse functions and compositions. If the inverse exists, then when you do f composed f inverse, you should get x. And because with function composition, order matters, you've got to also check the other direction, because they're not always the same thing. You might get x in one direction, but not the other, in which case they wouldn't be inverses. So check the composition the other way and see if you also get x. So that's how you check, and that's what this next theorem does. So to check if f and g are inverses, first find f of g of x, and if they're inverses, what's that going to have to equal?
G.
No,
So
x. To give you back x. If it gives you back x, then that direction's okay. If that doesn't give you x, then the functions are not inverses, unless you made a mistake. And then you check the other direction. You do g of f. And if they're inverses, this is also going to be x. So you check compositions in both directions, and if both directions give you x, then you know that they're inverses. So when I say check, that's what I mean. That's what we're going to do in example 5. So check and see whether this function and this function are inverses. Okay, so if we do f of g of x, that's f of, what goes in for g?
-5
And then that negative 5 over 2x plus 11, that goes in for that x, right? Okay, I'm going to do something a little bit wrong and tell me what's wrong. What did I forget? You need another set of parentheses. Yep, around that stuff. If you think my inputs always go in parentheses, that will actually always give you the right result. Okay, what happens to that negative sign when it distributes? What do you get inside those parentheses? 11.
+5.
And then, What cancels first?
11.
And then you have 2/5 times 5 halves x, and then 2/5 times 5 halves is just 1. So you just get, so in one direction you get x. 7? What? It's okay. All right, so one direction you get x. So maybe they're inverses. Now check the other. Find g of f. So g of 2/5 times 11 minus x, which is negative 5 over 2, times 2/5 times 11 minus x, plus 11. Does that plugging stuff in? Is that okay? When you multiply this 5 halves and that 2/5, what number comes out?
11 minus 6.
It's going to be positive 1 or negative 1? Negative 1. Times 11 minus x. And then what happens when that negative 1 distributes? What do you get? Well, you get negative 11 plus x plus 11, which then in the end gives you x. So, equals x. So yes or no, are these functions inverses? Yes, these functions are inverses. So, yeah.
Distribute the 2/5 to 11 minus x.
Oh, that would also work. Yep. That's officially the associative property of multiplication that works, that says that you can change the order in which you multiply things. So instead of grouping these two things multiplied first, I can do those two things and multiply them first. So if you do distribute the 2/5, you're going to get the same result, it just will look a little bit different in the intermediate steps. Okay. Another one. So determine whether these functions are inverses. So psychologically, the first one was yes, this one's probably no, right? But let's still show why. So f of g of x, that's f of cube root 3 minus x minus 1. And this stuff goes in for that x of f. So that's the thing that's been input. what happens to your ones? They cancel, and so you just have 2 minus the cube root of 3 minus x, and that whole thing is cubed. What does the cube root do to the cubed? They cancel, and you get 2 minus 3 minus x. Once again, the parentheses do actually matter. Okay, then distribute the negative. You get 2 minus 3 is, and then plus or minus x? Plus, okay. So does that composition equal just plain old x? No. These functions are not inverses. And because you know that the composition in one direction does not equal x, you don't even have to check the other. Does that make sense? Okay. All right, so here is how we find inverse functions, like finally. So the steps to find an inverse is first to find the domain of your function f and verify that f is 1 to 1. If f is not 1 to 1, stop, because f inverse does not exist. And something you should note is that sometimes the domains of functions are restricted to make the function 1 to 1. So for example, if you just took the right half of a parabola, all of a sudden that is a 1 to 1 function, and then it has an inverse. So sometimes domains are restricted to only mean part of a picture. Would the left half also be 1 to 1? It would, right? So technically speaking, if they have a restriction, it might be 1 to 1. Now what you do next is you replace your f of x by y, switch x and y, and then solve for y. The resulting equation you get is f inverse. This process of switching x and y and solving for y forces you to undo stuff in the correct order, because f did something to a number, and the inverse has to undo those things, right? But you've got to go backwards the original order. And then find the domain of f inverse and the range of f inverse. The domain of f inverse is the range of f, right? And then the range f inverse is domain of f, right? If you flip-flop the x's and y's, the domains and ranges have also flip-flopped. Okay, so let's actually find one of these for an easy function. So find f inverse for f of x is 1/3 x minus 5. So step 1 is, does this function pass the horizontal line test? Yeah, it's a line, slope 1/3, so yes, it passes the horizontal line test. Okay, what is the domain of f? Like, it looks roughly like this, right? So what is the domain of that function? All real numbers. What is the range of that function? All real numbers. Okay, so start by replacing f of x by y. So y is 1/3 x minus 5. Flip-flop the variables. X equals 1/3 y minus 5. And at this step, get the y alone. Solve for y. So in this particular case, how would you solve for y? Plus 5. X plus 5 equals 1/3 y. Times by 3. And that'd be 3 times the quantity x plus 5 equals y. Or y equals 3x plus how much? 15. Technically, it's best to say f inverse x, use function notation, 3x plus 15. Yes, you do have to do that last step, okay? Just replace y by f inverse. What's the domain of f inverse? All real numbers. What's the range of f inverse? All real numbers, yeah. Okay. Is everyone all right with how you find that? Okay, we'll do some harder ones as well, but that's kind of the simplest case. Okay, so how about this one? Find f inverse for f of x is root x plus 2. So first of all, is root x plus 2, roughly speaking, what does it look like?
Go back to
Check markish. Does that make sense? Okay, so does that function have an inverse? Yeah, it does. Okay. Looking at that picture, what is the domain of f? -2 to infinity. What is the range of f? So the lowest y value of that function is to infinity. So Tristan, writing stuff down might help you keep your eyes open, just FYI. Okay. Okay, so now replace the f of x by y. Flip-flop the x's and y's. And solve for y. What would you do first? Square both sides. So x squared would equal y plus 2. What would you do next? Subtract 2. X squared minus 2 equals y. So f inverse of x is x squared minus 2. There's only one slight issue. X squared minus 2 isn't 1-to-1, is it? So you have to restrict it. And the way you can tell how to restrict it is you find the domain and range of f inverse from the domain and range of f. Does that make sense? So for this thing, what's the domain gonna be? 0 to 2, which means you're, oh crap, not 0 to 2, 0 to infinity. That means you're only going to plug x's into that x squared minus 2 function if your x is bigger than 0. What's the range of f inverse? -2 to infinity. And you find those by flip-flopping the domain and range of f. That's the way to do that. So what that domain is saying is that x must be bigger than or equal to 0. And I think, I could be wrong, but I'm pretty sure that we also graphed these things when we found these compositions yesterday. Does that ring a bell? When we found compositions and we had these things that were actually inverses, but I didn't tell you they were inverses. We graphed them at the same time and they had that reflective pattern, right? If I were to graph x squared minus 2, it's half of a parabola down 2. Do you see that kind of symmetry going on there? The reflection over the diagonal? We did graph stuff like that, didn't we? Yeah, okay. All right, so there's another, so other than the domain restriction, finding the inverse wasn't very difficult, was it? Okay. So this next one, a lot like a question that was on your first test. So hey, great review. So find f inverse for f of x is x plus 1 over 3x minus 2. This one, you're going to have to take my word for it that this function is actually 1-to-1. So the problems in the book that are like this, they say the functions are 1-to-1, find their inverses. They just tell you that you're supposed to accept it and move on. Okay? So when you change this, so first it's y equals x plus 1 over 3x minus 2. When you flip-flop the x's and y's, what does it become? X equals... And you're going to have to solve for y. Does that look familiar? You did stuff like that, didn't you? Okay, so the first step was to multiply by 3y minus 2. So that's x times 3y minus 2 equals y plus 1. So you say multiply by 3y minus 2. Then you distribute, which gives you 3xy minus 2x equals y plus 1. So far, do you understand those two steps? Okay. Then the next step is the one that's a trick you're just going to have to figure out. get all things that have y, so all things with y on one side, all things with no y on the other. So if we're putting stuff that has y's in it on the left, what things are going to stay on the left? 3xy, and what else is going to be over there? Minus y. And everything that does not have a y gets shoved on the other side. So who are they? And, And then, once you've done that, you will have a GCF of y, which you can factor out. So that will become y times 3x minus 1. That is the trick that will make multiple y's to its first power all into 1. Okay, so that is on your retake if you have to do it. And so your final answer is y equals 2x plus 1 over 3x minus 1, right? Or f inverse of x is 2x plus 1 over 3x minus 1. Can you find the domain of f inverse just by looking at it? What's the one thing x cannot be? 1/3. Now the range of f would be y can't equal something.
2/3.
Yeah, and how did you find that? What did you look at?
First equation.
So look at domain of f. It's okay with me if on these questions you just tell me what x can't be and what y can't be. So if you want, you only have to give intervals if I've specified that you have to give intervals. Yeah.
I didn't quite hear what you said before. How'd you find the range?
So the range of f inverse is equal to the domain of the original function. So if you look at the original function, you find its domain. What is the one number that would make that denominator 0? So you would solve 3x minus 2 equal to 0. Does that make sense? And that'd be the one thing you'd have to leave out. The only difference is that in f inverse, it's a y, because the range is the set of all the y values. Does that make sense? Okay. Okay, and the final thing we're going to do before we move on to that last example from yesterday's lesson is just to graph a couple functions and their inverses and establish how they're related to each other. Okay, so graph the function f of x and its inverse. So root x squared minus 1, or root x minus 1. That's a root function shifted right 1. So it goes through 1, 1, 2, 1, and 1, 2, 3. There, that's the next point. Okay, so there's f. So f inverse is x squared plus 1, but there's this little restriction that x is bigger than or equal to 0, which means the only numbers you plug into it are positives. Yep. When you plug in 0, you get out 1. When you plug in 1, you get out 2. When you plug in 2, you get out plus 1 would make 5. And so there's f inverse. Or you could think it's the right half of a parabola that's been shifted up 1. And do you see a symmetry thing relating these two? Yeah, that if you were to, say, sketch in the diagonal, what's an equation for the line that is the diagonal? Y equals x, because it's a line with y-intercept 0 and slope 1, right? So we'll say f inverse is, or the graph of, we'll say, graph of f inverse is the graph of f reflected over y equals x. pretty easy to see there.
Is that how all inverses are?
All inverses work that way, yep. That comes from the fact that when you flip-flop x and y, those points end up reflecting over that line. Yep, so all inverses are like that. This one's really easy to see because the function is, the original function f is all on one side of the graph. The next one is a little bit different because they switch sides, but the picture is still the same, like relationship. So let's do one more. So x squared minus 4. So that's a parabola shifted down 4. And the x bigger than or equal to 0, does that mean the right half or the left half? This half, right? Okay. So down 4, 1, 2, 3, 4. There, where does it cross the x-axis? The y is 0, the x is 2. So there's your original function. Okay, how about the next one? This is a root function shifted how? Back 4. Is the reflection pattern still there? Yes. So this black part reflects up onto that purple part, right? And this part up here reflects down onto that. See that? It's just trickier to see when the function passes through that reflection line, but it does still have that reflexive property. So this is always true that the graph of f inverse is the graph of f reflected over y equals x. That's always true for every single pair of inverses. Once you've restricted domains, is that also, okay, so you have to first have a function that has an inverse. If you